Hello, fellow travelers, and welcome to the Sleepyhead Geographer. Tonight, we're going on a journey into the deepest places on our planet, where few have ventured and mysteries still await discovery. Let's close our eyes and imagine ourselves preparing for an expedition to one of Earth's most extraordinary and hidden realms, the Mariana Trench. Picture yourself settling into the comfortable seats of a research vessel as we begin our gentle voyage across the vast Pacific Ocean. The evening light dances on the water's surface, creating ripples of gold and amber that stretch toward the horizon like liquid metal, each wave catching and reflecting the dying sunlight in patterns that seem to pulse with the very heartbeat of the ocean. The air carries the distinctive scent of salt and seaweed, that ancient perfume that speaks to something deep in our evolutionary memory, reminding us that all life began in these waters billions of years ago. We're heading toward a place where the ocean floor plunges deeper than Mount Everest reaches high, a place where the earth itself opens up to reveal secrets that have been hidden for millions of years. The Mariana Trench lies in the western Pacific, stretching like a crescent moon across the ocean floor for over 1,500 miles, a vast underwater canyon that would dwarf any terrestrial feature if we could somehow drain the ocean and see it in its full majesty. But tonight, we're not just exploring a geographical feature. We're discovering a world within our world, a place where the familiar gives way to the extraordinary, where the very foundations of our planet tell stories of incredible forces, ancient collisions, and the endless dance between land and sea. This is a realm where our everyday understanding of pressure, temperature, and even life itself must be completely reconsidered, where the normal rules of existence bend and transform under conditions so extreme they might as well exist on an alien world. As we prepare to descend into these mysterious depths, let's take a moment to appreciate the magnitude of what we're about to explore. The deepest point of the Mariana Trench, known as Challenger Deep, plunges nearly 7 miles beneath the ocean's surface. So deep that if Mount Everest were placed at its bottom, the peak would still be over a mile underwater. Imagine stacking nearly 30 Empire State Buildings on top of each other, and you begin to grasp the vertical scale of this underwater cathedral. This is a place where pressure becomes unimaginable, where darkness reigns eternal, and where life has found ways to flourish in conditions that would seem impossible on the surface. The water pressure at the deepest point is over 1,000 times greater than at sea level. Imagine the weight of 50 jumbo jets pressing down on every square meter of surface. Yet remarkably, this crushing environment has become home to some of the most extraordinary creatures our planet has ever produced. Tonight, we'll journey together through the story of this remarkable abyss, from its violent formation millions of years ago to the cutting-edge explorations happening today. We'll meet the extraordinary creatures that call these depths home, organisms so perfectly adapted to their extreme environment that they represent evolutionary solutions to challenges that seem impossible to overcome. We'll understand the powerful geological forces that created this underwater canyon, processes so vast and patient that they operate on timescales that humble human understanding. We'll discover how this remote place continues to teach us about our planet, and perhaps even about life beyond Earth. The conditions in the Mariana Trench, the crushing pressure, eternal darkness, and unique chemistry may be some of the closest analogues we have on Earth to the environments that exist beneath the icy surfaces of moons like Europa and Enceladus, making our study of the trench crucial to our understanding of where life might exist elsewhere in the solar system. As we float peacefully on the surface, preparing for our imaginary descent, notice how the ocean around us seems to stretch infinitely in all directions. The surface waves that rock our vessel gently are just the most visible part of a vast, three-dimensional world that extends downward for miles. beneath our keel lies a column of water so tall that if it were solid, it would reach into the lower atmosphere. And at the very bottom of this liquid sky lies our destination, a place so remote and extreme that fewer people have visited it than have walked on the surface of the moon. The evening stars begin to appear overhead, their light reflecting off the water in dancing pinpoints of brilliance. These same stars have shone down on this patch of ocean for millions of years, their light penetrating only the first few hundred feet of water before being absorbed completely. Below that, in the realm we're about to explore, no natural light has ever penetrated. It is a world of eternal night, where the only illumination comes from the living creatures themselves, from the bioluminescent displays of deep-sea animals that create their own constellations in the abyss. So let's dim the lights of our imagination, take a deep breath of the salty sea air, and begin our peaceful descent into the Mariana Trench, Earth's deepest abyss, where every mile downward reveals new wonders and ancient secrets waiting to be told. Tonight we become explorers of the hidden depths, travelers into a realm that exists on our own planet, yet feels as foreign and wonderful as any world we might discover among the stars. Our story begins not in the depths of the ocean, but in the slow, powerful dance of the Earth's crust that has been choreographed over millions of years. Let's travel back in time, allowing our minds to drift to an era when the Pacific Ocean was taking shape and the forces that would create the Mariana Trench were just beginning their patient work. Imagine the Earth as it was roughly 180 million years ago, during the Jurassic period when dinosaurs roamed the land, and the very configuration of continents was dramatically different from today. The Atlantic Ocean was just a narrow sea, barely wider than the Mediterranean is now, while the Pacific stretched even more vastly across the globe than it does today. Beneath the ocean's surface, massive plates of rock, each one carrying continents and ocean floors, moved across the planet's surface like enormous, slow-moving rafts driven by convection currents deep within the Earth's mantle. Picture these tectonic plates as pieces of a vast, three-dimensional puzzle, each one dozens of miles thick and thousands of miles across. Unlike the rigid pieces of a conventional puzzle, however, these plates are in constant motion, driven by the heat generated deep within the Earth's core. The mantle beneath the plates churns in slow, massive convection cells, much like water boiling in an enormous pot, except this boiling takes place over millions of years and involves rock heated to temperatures of thousands of degrees. In the Western Pacific, two of these colossal plates began an encounter that would last for millions of years and continues to this day. The Pacific Plate, vast and ancient, was moving steadily westward at a rate of just a few inches per year, about the same rate that your fingernails grow. As it traveled, carrying with it the ocean floor, it encountered the smaller Philippine Sea Plate, and what happened next was a geological drama that unfolded with the patience of stone and the power of the entire planet. Visualize this meeting not as a sudden collision, but as a slow, inexorable embrace, where one plate gradually slides beneath another. The Pacific Plate, being older, cooler, and therefore denser than the Philippine Sea Plate, began to sink beneath it in a process geologists call subduction. Think of it like a massive conveyor belt of rock, slowly but continuously moving downward into the Earth's hot interior, where it would eventually melt and become part of the mantle once again, only to be recycled through volcanic activity elsewhere on the planet. This process of subduction is one of the fundamental mechanisms by which our planet recycles its surface materials. The oceanic crust that forms the Pacific Plate was originally created at mid-ocean ridges thousands of miles away, where volcanic activity continuously generates new seafloor. As this new crust moves away from the ridges where it was born, it gradually cools and becomes denser. By the time it reaches the edges of the Pacific, where it meets other plates, it has become heavy enough to sink back into the Earth's interior. As the Pacific Plate descended beneath the Philippine Sea Plate, it carved out a deep furrow in the ocean floor, the beginning of what we now know as the Mariana Trench. This wasn't a violent tearing or sudden rupture, but rather a gradual deepening, like water slowly carving a canyon over countless centuries, except here it was solid rock reshaping the very foundation of the ocean. The descending plate dragged with it the overlying sediments and even portions of the seafloor itself, creating a depression that grew deeper and longer with each passing millennium. Imagine standing on the ocean floor millions of years ago, if such a thing were possible, and watching this process unfold in fast forward. You would see the seafloor slowly bending downward, creating first a gentle depression, then a deeper valley, and eventually the profound abyss we know today. The process would appear smooth and continuous, but in reality it was punctuated by earthquakes as the descending plate occasionally stuck and then suddenly slipped deeper, releasing enormous amounts of energy in the process. The subduction process created something remarkable beyond just the trench itself. As the descending plate moved deeper into the earth, it carried with it sediments, seawater, and pieces of the ocean floor that had accumulated over millions of years. These materials, subjected to incredible heat and pressure as they descended, would sometimes melt and rise back toward the surface, creating volcanic activity that formed the Mariana Islands, the chain of volcanic peaks that parallels the trench and gives it its name. Picture these volcanic islands as they emerged from the sea, steam and lava creating new land, while, just a few dozen miles away, the ocean floor continued its patient descent into the abyss. The contrast is striking. While the trench represents the Earth swallowing its own surface, the volcanic islands represent the planet giving birth to new land. Both processes are driven by the same fundamental force, the subduction of the Pacific Plate, creating a landscape of extraordinary geological drama. The formation of the Mariana system illustrates one of the most elegant principles of plate tectonics, the balance between creation and destruction. For every square mile of new oceanic crust created at mid-ocean ridges, an equivalent amount must be destroyed through subduction. The Mariana Trench serves as one of the planet's great recycling centers, where old seafloor returns to the mantle to be reprocessed and eventually reformed as new crust elsewhere. Let's envision the immense forces involved in this process. The Pacific Plate that's being subducted weighs billions upon billions of tons, yet it moves with the steady persistence of gravity and heat. The pressure exerted by the descending plate is so great that it can literally squeeze water out of rock, creating conditions deep within the Earth that drive volcanic activity hundreds of miles away. The plate itself, as it descends, generates earthquakes that can be felt across the entire Pacific basin. The trench was growing deeper and longer with each passing age, reaching toward what would eventually become its maximum depth of nearly 36,000 feet below sea level. But this deepening wasn't uniform. Some sections of the trench developed more rapidly than others, creating the complex topography we see today. The interplay between the rate of subduction, the amount of sediment being deposited, and the resistance of different types of rock created a varied landscape of ridges, valleys, and basins within the larger trench system. This ongoing subduction has continued for millions upon millions of years, and it continues today. The Pacific Plate still moves westward at its patient pace, carrying with it the seafloor and everything that lives upon it. In the deepest parts of the trench, pieces of seafloor that formed when dinosaurs ruled the Earth are still slowly making their way into the planet's interior. While on the ocean surface above, whales migrate and storms rage, completely unaware of the vast geological drama unfolding in the depths below. As we envision this ancient and ongoing process, we can almost feel the immense patience of the Earth itself, the way geological time moves in rhythms far slower than human experience, yet with a consistency and power that reshapes entire ocean basins. A human lifetime is just a brief moment in the story of the Mariana Trench, yet the same processes that have operated for millions of years continue to shape and deepen this remarkable feature. The birth of this abyss teaches us about the dynamic nature of our planet, how the solid ground beneath our feet and the seemingly permanent ocean floors are actually part of a continuous, slow-motion dance of creation and destruction. The Earth's surface is not fixed and unchanging, but rather a dynamic system where old materials are constantly being recycled back into the planet's interior, while new materials are brought to the surface through volcanic activity. Understanding the formation of the Mariana Trench also helps us appreciate the interconnectedness of geological processes. The same forces that created this deepest place on Earth are responsible for the formation of mountain ranges, the occurrence of earthquakes, and the distribution of volcanic activity around the Pacific Ring of Fire. The trench is not an isolated feature, but part of a global system of plate movements that shapes our entire planet. As our imaginary time machine brings us forward through the millions of years, we can watch the trench deepen and mature, becoming the profound abyss that beckons to us today. The same forces that created it continue to shape it, ensuring that the Mariana Trench remains not just a relic of ancient geological processes, but a living, evolving feature of our dynamic planet. Even as we explore it today, it continues to change, to deepen, and to reveal new aspects of its complex character with each passing century. Now that we understand how the Mariana Trench came to be, let's explore its remarkable structure and discover the intricate architecture of this underwater world. As we begin our imaginary descent from the ocean's surface, we'll notice how the trench reveals itself in layers, each with its own character and secrets, like reading the chapters of an enormous book written in stone and sediment. The Mariana Trench stretches approximately 1,580 miles in a graceful arc across the Pacific Ocean floor, resembling a crescent moon when viewed from above. To appreciate this scale, imagine a canyon stretching from New York City to Denver, except this canyon lies beneath nearly 7 miles of water and reaches depths that would challenge our deepest terrestrial gorges. But its most remarkable feature isn't its length, it's its extraordinary depth and the complex topography that lies hidden beneath the waves. Let's envision ourselves in a state-of-the-art submersible, beginning our descent from the surface of the Pacific on a calm, clear day. The morning sun filters down through the crystal-clear tropical waters, creating columns of light that dance and shimmer as they penetrate the blue. Schools of yellowfin tuna streak past like living torpedoes, their silver sides flashing in the filtered sunlight, while above us, the surface of the ocean creates a ceiling of rippling liquid silver. As we sink through the first few hundred feet, we're still in the euphotic zone, where sunlight provides enough energy for photosynthesis. Here, microscopic phytoplankton drift like underwater snow, their tiny bodies converting sunlight and carbon dioxide into the organic matter that forms the foundation of all ocean life. The water around us teems with activity. Jellyfish pulse through the water with ethereal grace, their translucent bodies catching and scattering the light, while small fish dart between trailing tentacles in elaborate games of survival. Continuing our descent past 600 feet, we enter the twilight zone, where the last traces of sunlight begin to fade into blue-black obscurity. The water here takes on an indigo hue, deep and mysterious, while the pressure around our submersible begins to increase noticeably. Our instruments register the changing conditions, temperature dropping steadily, pressure increasing with mathematical precision, and the dissolved oxygen content of the water beginning to decline as we move away from the surface where gas exchange with the atmosphere occurs. As we descend past 3,000 feet, we enter what oceanographers call the bathyal zone, and here we encounter the trench's outer slopes for the first time. These aren't the steep, cliff-like walls you might imagine from terrestrial canyons, but rather gentle inclines that slope downward at angles of about 7 to 10 degrees. Picture rolling underwater hills covered in fine sediment, creating a landscape that feels both alien and oddly familiar, like a terrestrial countryside transformed into an aquatic dreamscape and painted in shades of grey and brown. The sediment covering these slopes tells a story that spans millions of years. Each grain represents a tiny piece of Earth's history, microscopic shells of marine organisms that lived and died in the waters above, dust particles blown from distant continents, volcanic ash from eruptions that occurred thousands of miles away, and even particles from meteorites that struck the Earth eons ago. This sedimentary blanket, in some places hundreds of feet thick, preserves a record of our planet's past climate, volcanic activity, and biological evolution. The walls of the trench tell stories written in layers of sediment and rock, exposed by the ongoing process of subduction. Some areas reveal exposed sections of the ocean crust itself. Ancient basalt formed millions of years ago at mid-ocean ridges, now tilted and fractured by the immense tectonic forces. These dark volcanic rocks, originally formed in the fiery heat of underwater eruptions, now lie exposed like the bones of the Earth, weathered by the slow but persistent chemistry of seawater. Other sections show thick accumulations of sediment that have been compressed and folded by the tremendous forces involved in plate subduction. These sedimentary layers, originally deposited as horizontal sheets on the ocean floor, have been twisted and contorted into complex patterns that resemble abstract art painted on the walls of an underwater cathedral. Geologists reading these patterns can decipher the history of the region, understanding how the forces of subduction have changed over time. As we continue our descent into ever deeper water, the trench reveals its complex inner structure. It's not simply one enormous canyon, but rather a series of interconnected basins, ridges, and sub-trenches. Imagine a vast underwater mountain range turned inside out, where instead of peaks reaching toward the sky, we have valleys and chasms reaching toward the Earth's core. Each basin has its own character, its own sediment patterns, and its own community of deep-sea life adapted to the specific conditions found there. The topography becomes increasingly complex as we descend. Underwater ridges divide the trench into separate basins, creating a landscape of extraordinary diversity. Some of these ridges rise thousands of feet from the surrounding seafloor, creating underwater mountains that have never seen sunlight. Their slopes are covered with fine sediment that has accumulated grain by grain over millions of years, while their peaks may be swept clean by deep ocean currents that flow through the trench system like underwater winds. Between these ridges lie deep basins filled with the finest sediments, particles so small they can remain suspended in the water for years before finally settling to the bottom. These basins act like sediment traps, collecting the organic and inorganic debris that rains down from the waters above. The sediment in these basins can be hundreds of feet deep, creating soft, muddy plains that extend for miles in the eternal darkness. The deepest part of our journey takes us to Challenger Deep, located in the southern portion of the trench near the island of Guam. Here, the sea floor plunges to depths of nearly 36 to 200 feet, or about 6.8 miles, below sea level. To put this extraordinary depth in perspective, if we could somehow drain all the water from this part of the ocean, we would see a chasm deeper than the Grand Canyon, Mount Washington, and the Willis Tower stacked on top of each other. But Challenger Deep isn't a single point. It's actually a small valley on the trench floor, roughly 8 miles long and 1 mile wide. Picture a bathtub-shaped depression at the bottom of an already impossibly deep canyon, with gently sloping sides leading down to a relatively flat floor. This deepest place on Earth's surface is covered with a layer of fine sediment that has accumulated over thousands of years, creating a soft, muddy bottom that records the history of everything that has fallen into the abyss. The walls of Challenger Deep rise around this central depression like the sides of a vast amphitheater. These slopes, covered in fine sediment and occasional rockfalls from higher up the trench walls, create a landscape that changes constantly, though imperceptibly by human standards. Every few decades or centuries, underwater landslides reshape portions of these walls, while the ongoing process of sedimentation slowly fills in the deepest areas, only to have them deepened again by continuing tectonic activity. The trench's architecture includes fascinating features that scientists are still discovering with each new expedition. There are underwater cliffs, thousands of feet high, their vertical faces scarred by rockfalls and carved by underwater currents. Mysterious pools of liquid sulfur created by chemical reactions between seawater and the rocks beneath collect in some of the deepest basins. Areas where the seafloor is cracked and fractured create complex mazes of smaller canyons and ridges, each with its own micro-environment and unique community of deep-sea life. Some sections contain what geologists call accretionary wedges, areas where sediment scraped off the descending Pacific plate has been compressed and folded into underwater mountain ranges. These features, invisible from the surface but clearly revealed by sonar mapping, create complex topography that can extend for hundreds of miles along the trench system. The sediments in these wedges have been compressed to incredible densities, creating rock-like formations from what was once soft ocean floor mud. One of the most intriguing aspects of the trench's structure is its variability along its great length. As we move along the trench from north to south, the depth changes dramatically. Some sections are only 20,000 feet deep, still deeper than any terrestrial canyon, while others plunge much deeper toward the ultimate depths of Challenger Deep. This variation tells us about the complex interplay of geological forces, the age of different sections, and the varying rates of sediment accumulation over time. The northern sections of the trench, closer to Japan, show evidence of more recent volcanic activity, with fresh lava flows and active hydrothermal vents creating oases of heat and chemical activity in the cold, dark depths. Moving south toward the Philippines and Guam, the trench deepens, and the seafloor shows the accumulated effects of millions of years of sedimentation and tectonic activity. Throughout the trench system, we find evidence of ongoing geological activity. The seafloor here isn't static, but continues to shift and change in response to the forces of subduction. Underwater landslides have carved new features into the trench walls, triggered by earthquakes or the simple accumulations of too much sediment on unstable slopes. These landslides can move millions of tons of sediment in a matter of hours, creating underwater avalanches that reshape the seafloor and bury existing ecosystems under layers of displaced material. Scientists have discovered that parts of the trench floor are actually moving horizontally as well as vertically, creating a three-dimensional puzzle of geological motion. GPS-like measurements taken by instruments on the seafloor show that different parts of the trench are moving in different directions as the complex forces of subduction pull and push on the ocean floor. This movement, though measured in inches per year, adds up to significant changes over geological time. The sediments that blanket much of the trench floor create their own topographic features, sculpted by forces we rarely consider. In some areas, these fine particles have been shaped by deep ocean currents into underwater dunes and ripples, creating patterns that mirror those we might see in a desert, but formed by the gentle, persistent flow of water instead of wind. These current-formed features can extend for miles, creating vast fields of sedimentary sculptures in the darkness of the deep. Deep ocean currents flowing through the trench system like underwater rivers create their own geological effects. These currents, driven by differences in water temperature and density, can flow for thousands of miles across the ocean floor. Where they encounter the walls of the trench, they create erosional features, underwater valleys and channels carved by the persistent flow of water carrying fine sediments. Some areas of the trench floor are marked by the presence of pockmarks, circular or elliptical depressions created by the escape of gases or fluids from beneath the sea floor. These features, ranging from a few feet to hundreds of yards across, indicate ongoing chemical and biological processes occurring within the sediments. Some pockmarks are associated with cold seeps, where hydrocarbons leak slowly from the seafloor, creating unique chemical environments that support specialized communities of microorganisms. The three-dimensional structure of the Mariana Trench creates a complex system of water circulation that affects everything from the distribution of nutrients to the movement of deep-sea organisms. Water trapped in the deepest basins can remain isolated for decades or centuries, developing unique chemical signatures that tell scientists about the long-term processes occurring in these remote environments. As we imagine ourselves exploring this vast underwater architecture, we begin to appreciate that the Mariana Trench is far more than just the deepest place on Earth. It's a complex, dynamic landscape with its own weather patterns, geological processes, and topographic diversity. Every ridge, valley, and slope in this underwater realm has been shaped by forces acting over immense periods of time, creating a hidden world of breathtaking complexity and beauty that challenges our understanding of what landscapes can be. As our imaginary submersible continues its descent into the Mariana Trench, we begin to encounter conditions so extreme they challenge our understanding of what life is possible. Let's pause in our journey to appreciate the remarkable environment that characterizes Earth's deepest places, where the familiar laws of our surface world give way to something altogether more extraordinary and alien. Picture yourself at a depth of 20,000 feet, still miles above the deepest point of the trench, but already in a realm that feels utterly foreign. Here, the water pressure is already 60 times greater than what we experience at sea level. To truly understand this immense force, imagine the weight of a small automobile pressing down on every square inch of surface. That's the force pressing against every part of our submersible's hull from all directions simultaneously. Now, as we continue deeper toward Challenger Deep, that pressure increases relentlessly, reaching more than 1,000 times sea level pressure at the bottom, equivalent to having 50 jumbo jets stacked on top of every square meter. This crushing pressure would instantly compress any air-filled space to a tiny fraction of its original size. A foam coffee cup lowered to these depths would emerge no larger than a thimble, compressed into a dense, hard pellet by the relentless squeeze of the water above. A balloon filled with air at the surface would shrink to invisibility, its air compressed to liquid density. Even the hull of our submersible, made from the strongest titanium alloys and forged to incredible precision, creaks and groans under the enormous stress. Yet remarkably, this isn't the violent, destructive force we might imagine. Instead, it's a constant, even pressure that creates its own unique environment, one where different rules apply and different possibilities emerge. The pressure doesn't attack from one direction like a crushing weight, but embraces everything equally from all sides, creating a stable, if extreme, environment where life has learned to thrive. The darkness at these depths is absolute and eternal, a blackness so complete it has no parallel in our surface experience. No photon of sunlight has ever penetrated to the bottom of the Mariana Trench. This isn't simply the darkness of a moonless night. where our eyes might gradually adjust and pick out shapes and shadows, or even the darkness of a cave, where some light might filter in from distant openings. This is a complete absence of light that has persisted for millions of years, creating an environment where the concept of day and night has no meaning, where the cycle of seasons marked by changing sunlight is completely irrelevant. In this perpetual darkness, the only light comes from life itself. Bioluminescence, the ability of living organisms to create light through chemical reactions, becomes not just an adaptation, but an essential tool for survival. Deep-sea creatures create their own constellations in this liquid space, flashing messages to potential mates, startling predators with sudden displays of light, or using bioluminescent lures to attract prey. The darkness isn't empty. It's filled with the gentle light show of countless organisms, each one a tiny star in this underwater galaxy. In this perpetual darkness, temperature becomes another defining characteristic of the deep-sea environment. Despite being in the tropics, where surface waters are warm and inviting, reaching temperatures that would be comfortable for a tropical vacation, the bottom of the trench maintains a temperature just slightly above freezing, around 34 to 39 degrees Fahrenheit. This cold water has traveled an incredible journey to reach these depths, originating in the polar regions where surface water, cooled by contact with Arctic air and ice, becomes dense enough to sink to the ocean floor. Imagine this water beginning its journey in the frigid seas around Antarctica or the Arctic Ocean, chilled by months of contact with ice and snow. As this cold, dense water sinks, it begins an epic voyage across the ocean floor, flowing in massive, slow-moving currents that can take decades or even centuries to complete their journey. These deep currents, invisible from the surface but carrying enormous volumes of water, connect the deepest trenches to the polar regions thousands of miles away. But even in this cold darkness, the trench isn't entirely without heat. In certain areas, geological activity creates surprising pockets of warmth that transform the deep-sea environment completely. Hydrothermal vents, where hot water springs from cracks in the seafloor, can create oases of warmth in the frigid deep, with water temperatures reaching hundreds of degrees Fahrenheit just inches away from the near-freezing ambient water. These vents occur where seawater seeps down through cracks in the oceanic crust, penetrating deep into the rock where it encounters the heat generated by geological processes. The water becomes superheated, dissolving minerals from the surrounding rock, and then rises back to the seafloor under pressure, carrying these dissolved compounds back to the deep-sea environment. As this hot, mineral-rich water meets the cold seawater, the dissolved minerals precipitate out, creating chimney-like structures that can grow dozens of feet tall. The chemistry of the deep trench water tells its own fascinating story of the connections between Earth's surface and interior. At these depths, the water contains very little dissolved oxygen, most of it having been consumed by marine life during the water's long journey from the surface. Instead, the water is rich in carbon dioxide, which has accumulated as organic matter from the surface waters above decomposes in the deep. This creates a slightly acidic environment that affects everything from the shells of deep-sea creatures to the chemistry of the sediments on the seafloor. The immense pressure also affects how gases behave in ways that seem almost magical compared to our surface experience. Carbon dioxide that would form bubbles and rise rapidly to the surface at sea level pressure remains dissolved in the water at these depths, creating unusual chemical conditions. Even more remarkably, under the extreme pressure of the deepest parts of the trench, some gases can actually become denser than water and form layers on the seafloor, creating underwater lakes of liquid gas. One of the most fascinating aspects of this extreme environment is how it affects the fundamental properties of water itself. Under such enormous pressure, water becomes significantly denser, about 5% denser than at the surface, and its behavior changes in subtle but important ways. The increased density affects how sound travels, how heat is conducted, and even how dissolved substances interact with each other. The pressure is so great that it affects the molecular structure of the water, making it behave almost like a different substance than the familiar water we know at the surface. The viscosity of water changes under these extreme conditions as well, becoming slightly thicker and more resistant to flow. This affects everything from how deep-sea creatures move through the water to how particles settle to the seafloor. What seems like a minor change in the laboratory becomes significant over the vast scales of deep ocean processes. Sound travels differently in this deep environment, and the acoustic properties of the trench create an underwater sound channel unlike anywhere else on Earth. The combination of intense pressure, low temperature, and unique water chemistry creates conditions where certain frequencies of sound can travel for enormous distances through the deep water. The trench can act like a vast acoustic waveguide, allowing sounds to propagate across entire ocean basins, carrying information about earthquakes, underwater landslides, and even the calls of deep-sea animals across thousands of miles. Low-frequency sounds, in particular, can travel incredible distances in the deep ocean, and scientists use this property to study geological processes and monitor changes in the deep-sea environment. The trench itself can generate sounds, the creaking and groaning of rock under stress, the rumble of underwater landslides, and the hiss of gases escaping from the seafloor, creating an acoustic environment that would be completely alien to our surface-dwelling ears. The seafloor itself, under such tremendous pressure, behaves differently than we might expect based on our terrestrial experience. The sediments are compressed into incredibly dense layers, squeezed by the weight of miles of water above until they take on properties more like soft rock than the loose mud we might imagine. Even the rocks of the oceanic crust are squeezed and compacted, their mineral structures altered by the enormous pressures. This compression affects everything that lives in or on the seafloor sediments. Bacteria and other microorganisms must adapt not only to the crushing pressure, but also to the unique properties of these compressed sediments. The spaces between sediment grains, which at the surface might be filled with air or water, are compressed to almost nothing, creating an environment where the normal rules of microbial ecology must be completely rewritten. Perhaps most remarkably, this seemingly hostile environment experiences its own form of weather, though it operates on timescales that dwarf our familiar meteorological cycles. Deep ocean currents flow through the trench, carrying nutrients, sediments, and even oxygen from distant parts of the ocean. These currents can create underwater storms of sorts, stirring up sediments and creating changes in the deep environment that unfold over months or years rather than hours or days. These deep-sea weather patterns are driven by differences in water density caused by variations in temperature and salinity. When dense water from one region encounters less dense water from another, it can create current systems that flow for thousands of miles across the ocean floor. These currents can speed up and slow down, change direction, and even create underwater turbulence that affects the distribution of nutrients and organisms in the deep sea. The Mariana Trench also experiences something like seasonal changes, though they're driven not by the sun, but by surface ocean conditions thousands of miles above and months or years in the past. When plankton blooms occur in the surface waters, the organic material that eventually sinks to the trench floor can create brief periods of increased biological activity in the deep, like a gentle rain of nutrients falling into this underwater desert. This marine snow, the constant shower of organic particles drifting down from the productive surface waters, represents the primary connection between the sunlit world above and the dark realm of the deep trench. The particles fall slowly through the water column, taking weeks or months to complete their journey from surface to seafloor. By the time they reach the bottom, they've been partially decomposed by bacteria in the water column, but they still carry essential nutrients that support the deep-sea ecosystem. The chemical environment of the deep trench is further complicated by the presence of dissolved minerals that have accumulated over millions of years. The water contains high concentrations of silica dissolved from the shells of microscopic marine organisms and various trace metals that have been leached from the surrounding rock. These dissolved substances create a unique chemical signature that can be detected by sensitive instruments, allowing scientists to trace the movement of water masses and understand the complex circulation patterns of the deep ocean. Temperature gradients within the trench create their own microenvironments. While the bottom water may be uniformly cold, areas near hydrothermal vents can experience temperature variations of hundreds of degrees over distances of just a few feet. These thermal boundaries create chemical gradients where different types of organisms can thrive, each adapted to its particular combination of temperature, pressure, and chemical conditions. The extreme environment of the Mariana Trench also creates unique preservation conditions that act like a natural time capsule. Organic matter that reaches the deep seafloor can be preserved for thousands or even millions of years in the cold, oxygen-poor conditions. This means that the sediments of the trench contain detailed records of past climate conditions, ocean chemistry changes, and even the history of life in the overlying waters. As we contemplate this extreme environment, we begin to understand that the Mariana Trench represents conditions that exist nowhere else on our planet's surface. The combination of crushing pressure, eternal darkness, near-freezing temperatures, and unique chemistry creates an environment that is perhaps the closest we can come to experiencing truly alien conditions without leaving Earth. Yet remarkably, as we'll soon discover, this apparently hostile environment has become home to some of the most extraordinary life forms our planet has ever produced. The pressure, darkness, cold, and unique chemistry that characterize the deep trench haven't created a sterile, empty world, but rather an environment that has pushed life to evolve in ways that challenge our basic assumptions about what's possible. In this alien realm beneath our familiar ocean, life has found not just ways to survive, but ways to thrive, creating an ecosystem that operates by rules fundamentally different from those that govern life in the sunlit world above. As we continue our gentle descent into the deepest parts of the Mariana Trench, we might expect to find a lifeless void, a sterile world where the extreme conditions have eliminated any possibility of biological activity. But prepare to be amazed, for the deep trench harbors some of the most extraordinary life forms on Earth, creatures so perfectly adapted to their extreme environment that they seem like visitors from another planet. Yet they represent some of the most ancient and successful evolutionary experiments our world has ever produced. Let's imagine ourselves exploring the muddy sediments of the trench floor, our submersible's powerful lights piercing the eternal darkness to reveal the first signs of life. The beams of our lights, cutting through water that has never known sunlight, illuminate a landscape that initially appears barren and lifeless. The seafloor stretches away into darkness in all directions, covered with fine sediment that has the consistency of thick mud, colored in shades of brown and gray that speak of organic matter mixed with mineral particles from the world above. But as our lights play across this seemingly empty landscape, and our instruments begin their careful analysis, we discover that this apparent wasteland is actually teeming with life. In the soft ooze that covers much of the seafloor, we discover countless tiny organisms that have learned not just to tolerate the extreme conditions, but to thrive under pressures that would instantly crush most surface life. These are the extremophiles, life forms that don't just endure extreme conditions, but actually require them to survive and reproduce. Among the most remarkable residents of the deep trench are the barophiles, organisms that have adapted specifically to high-pressure environments. These microscopic bacteria and archaea, invisible to the naked eye but present in enormous numbers, have developed unique cellular structures that not only withstand the crushing pressure but actually depend on it for their biological processes. Their cell membranes are composed of special fats and proteins that remain flexible under conditions that would turn normal cellular structures into rigid, non-functional masses. Remove them from their high-pressure home and bring them to the surface, and they would die as quickly as a surface fish would perish in the depths. Picture these microscopic pioneers, so small that millions could fit in a teaspoon of sediment, yet so sophisticated that they've solved biological puzzles that scientists are only beginning to understand. Their proteins are folded in unique three-dimensional configurations that maintain their function despite the crushing environment. Some of these proteins are so specialized that they actually require high pressure to maintain their proper shape. They would unfold and become useless in the low-pressure environment of the surface world. These deep-sea bacteria have also evolved remarkable metabolic pathways that allow them to derive energy from chemical compounds that would be toxic to most surface life. Some species process sulfur compounds, others metabolize methane, and still others can derive energy from the breakdown of complex organic molecules that have drifted down from the surface world. They represent some of the oldest forms of life on Earth, similar to the organisms that may have first evolved in our planet's ancient oceans when the atmosphere contained no oxygen and life had to find other ways to generate energy. But the microscopic world is just the beginning of life in the abyss. As our lights scan across the trench floor, we encounter larger, more complex creatures that seem to defy our understanding of how life should work under such extreme conditions. Here we find amphipods, tiny, shrimp-like creatures no bigger than your thumb, that have been discovered even in the deepest parts of Challenger Deep, living at pressures that were once thought to be incompatible with complex multicellular life. These deep-sea amphipods, with their ghostly, translucent appearance and delicate movements, represent some of the deepest living animals ever discovered. Their bodies are like living jewels in the darkness, their translucent shells revealing internal organs that pulse with life. They've evolved remarkable adaptations that allow them to function in their extreme environment. Special proteins that prevent their cellular structures from being damaged by the extreme pressure, efficient digestive systems that can process the scarce food that reaches these depths, and reproductive strategies that ensure the survival of their species in one of Earth's most challenging environments. These tiny creatures often feed on the organic matter that slowly drifts down from the world above, a process scientists call marine snow. This constant, gentle shower of organic particles, including dead plankton, fecal pellets from surface animals, and fragments of larger organisms, represents the primary food source for most deep-sea life. The amphipods have evolved efficient ways to capture and process this nutritional rainfall, often supplementing it by feeding on bacteria and other microorganisms that live in the sediment. Moving through the water column above the seafloor, we encounter other remarkable creatures that have adapted to life in the crushing depths. Comb jellies, transparent, ethereal animals that propel themselves through the water with rows of beating cilia that create rainbow patterns in our lights, drift through the darkness like living crystals. Their gelatinous bodies are perfectly adapted to the high-pressure environment, and their bioluminescence serves multiple purposes: communication with potential mates, defense against predators, and perhaps simply the beautiful expression of life persisting in the most unlikely places. These comb jellies create their own light shows in the darkness, their bodies flashing with waves of blue and green bioluminescence that pulse along their transparent forms. When disturbed by our submersible's movements, they respond with cascades of light that illuminate the surrounding water, creating a display that rivals any fireworks show on the surface world. Their ability to create light in this eternally dark environment represents one of evolution's most elegant solutions to the challenge of communication in a world without sun. The trench is home to several species of snailfish, remarkable vertebrates that have been found living at depths where scientists once thought complex life was impossible. These fish, with their gelatinous bodies and oversized heads, represent the deepest living vertebrates known to science. They've evolved antifreeze proteins in their blood to prevent ice crystal formation in the near-freezing water, specialized pressure-resistant cell membranes that maintain their integrity under crushing conditions, and unique bone structures that are flexible enough to withstand the enormous pressure while still providing structural support. The deepest living snailfish discovered so far was found at depths exceeding 26,000 feet, deeper than Mount Everest is tall. These ethereal creatures, with their translucent bodies and large, dark eyes, adapted for life in perpetual darkness, seem to float through the water like underwater ghosts. Their movements are slow and deliberate, conserving energy in an environment where food is scarce and every calorie must be carefully managed. One of the most fascinating aspects of deep trench life is how these creatures have solved the problem of reproduction in such an isolated and challenging environment. Many deep-sea animals have evolved hermaphroditic capabilities. They can function as both male and female, which dramatically increases the chances of successful reproduction when potential mates are few and far between. This adaptation ensures that any two individuals of the same species that encounter each other can potentially produce offspring, maximizing reproductive success in the sparse population densities of the deep sea. Others have developed elaborate chemical communication systems, releasing pheromones into the water to attract distant partners across the vast expanses of the deep sea floor. These chemical signals can travel for miles through the water, carried by deep ocean currents to reach potential mates that might otherwise never encounter each other in the darkness of the abyss. The food webs in the deep trench represent evolutionary ingenuity at its finest, showcasing life's ability to adapt to the most challenging conditions. In the absence of sunlight and photosynthesis, life here depends on chemosynthesis, the process by which certain bacteria convert chemical compounds like hydrogen sulfide, methane, and ammonia into energy. These chemical-eating bacteria form the foundation of the trench's food web, serving the same role that photosynthetic plants and algae play in surface ecosystems. The chemosynthetic bacteria that thrive in the deep trench have evolved to exploit chemical energy sources that would be toxic to most surface life. Some species process sulfur compounds that seep from the seafloor, others metabolize methane that bubbles up from deep within the sediments, and still others can derive energy from the breakdown of organic compounds that have accumulated in the deep-sea mud over thousands of years. Near hydrothermal vents in the trench, we encounter some of the most spectacular examples of deep-sea life. These underwater oases, where hot, mineral-rich water erupts from the seafloor, support ecosystems that rival tropical rainforests in their diversity and productivity. Giant tube worms, some growing over 6 feet long, sway gently in the warm currents from the vents, their bright red plumes filtering nutrients from the water. These remarkable tube worms have no digestive system of their own. Instead, they host symbiotic bacteria in specialized organs within their bodies. These bacteria process chemicals from the hydrothermal vents, primarily hydrogen sulfide, and convert them into organic compounds that nourish their enormous hosts. This partnership between the tube worms and their bacterial symbionts represents one of the most successful evolutionary solutions to life in the deep sea, allowing complex multicellular organisms to thrive in an environment where traditional food sources are scarce. The hydrothermal vent communities also include other remarkable organisms. Ghostly white crabs that scavenge around the vents, their pale shells reflecting our submersible's lights. Bizarre scale worms with iridescent scales that catch and reflect the bioluminescent displays of other deep-sea creatures. And peculiar snails that graze on bacterial mats covering the rocky surfaces around the vents. The deep trench is also home to various species of sea cucumbers, soft-bodied echinoderms that crawl slowly along the seafloor like underwater vacuum cleaners. These creatures, some reaching lengths of several feet, serve as the trench's cleanup crew, processing sediment and extracting nutrients from the organic matter mixed within. They move across the seafloor in slow motion, ingesting sediment through their mouths and extracting any available organic material before expelling the processed sediment in neat piles behind them. These sea cucumbers play a crucial ecological role in the deep trench, recycling nutrients and maintaining the health of their deep-sea ecosystem. Their constant processing of seafloor sediments helps to oxygenate the upper layers of the seabed and makes nutrients available to bacteria and other microorganisms that live within the sediment. Perhaps most remarkably, scientists have discovered that the deepest parts of the ocean trenches may serve as repositories of genetic diversity, unlike anywhere else on Earth. The isolation of these environments, separated from other deep-sea habitats by vast expanses of shallower water, has allowed unique evolutionary experiments to unfold over millions of years. Each trench system around the world has developed its own endemic species, creatures that exist in only one specific deep-sea location and nowhere else on the planet. This endemism means that each deep-sea trench is like a separate evolutionary laboratory, where life has independently found solutions to the challenges of extreme depth, pressure, and isolation. The Mariana Trench alone is home to dozens of species that exist nowhere else, and scientists estimate that many more remain to be discovered. Recent discoveries have revealed that life in the Mariana Trench is far more diverse and abundant than previously imagined. Advanced sampling techniques and improved underwater vehicles have allowed scientists to collect specimens and observe behaviors that were impossible to study just a few decades ago. Each expedition to the deep brings back new species, and genetic analysis often reveals that what appeared to be one species is actually several closely related species that have evolved subtle differences in response to the specific conditions of different parts of the trench. Some researchers estimate that the deep ocean trenches may contain more unique species per unit area than many tropical rainforests. This extraordinary biodiversity is hidden beneath miles of water in eternal darkness, representing one of the last great unexplored frontiers on our planet. Every sample of sediment from the trench floor contains dozens of species of bacteria and other microorganisms, many of which are new to science. The study of life in the Mariana Trench has profound implications for our understanding of life's possibilities beyond Earth. If complex organisms can thrive under such extreme conditions, crushing pressure, eternal darkness, near-freezing temperatures, and toxic chemical conditions, it dramatically expands our conception of where life might exist elsewhere in the universe. The icy moons of Jupiter and Saturn, with their deep oceans hidden beneath frozen surfaces, suddenly seem much more promising as potential habitats for life. The discoveries in the Mariana Trench have also revolutionized our understanding of the limits of life on Earth. Each new expedition pushes deeper into the trench and discovers life thriving at depths and pressures that were previously thought to be incompatible with complex organisms. These findings suggest that life may exist in other extreme environments on Earth that have not yet been fully explored. In the deep subsurface, in highly acidic or alkaline environments, or at temperatures and pressures that challenge our current understanding of biological limits. As we observe these remarkable creatures in their deep-sea home, floating in our imaginary submersible as they go about their ancient routines in the darkness, we're reminded that life on Earth is far more resilient, creative, and persistent than we often realize. In the crushing depths of the Mariana Trench, in conditions that would seem hostile to any form of existence, life has not merely survived, it has flourished, diversified, and created some of the most extraordinary adaptations in the biological world. These deep-sea organisms represent evolutionary solutions that have been tested and refined over millions of years, creating biological systems so efficient and well-adapted that they offer insights into everything from biotechnology to astrobiology. The proteins that allow deep-sea bacteria to function under extreme pressure are being studied for industrial applications, while the symbiotic relationships between tube worms and chemosynthetic bacteria provide models for understanding how life might function in the absence of solar energy on other worlds. The human fascination with the Mariana Trench began long before we had the technology to explore it, rooted in our species' fundamental curiosity about the unknown and our irrepressible drive to push beyond the boundaries of the possible. For centuries, sailors crossing the Pacific Ocean knew they were traveling above profound depths, but the true extent of the abyss remained one of Earth's greatest mysteries, as remote and inaccessible as the surface of another planet. Let's trace the remarkable human quest to reach the bottom of the world, a journey that has required pushing the boundaries of engineering, courage, and our understanding of what's possible. This story is not just about technological achievement, but about the profound human desire to explore and understand our world, to venture into places where no one has gone before, and to answer the fundamental questions about what lies hidden in the deepest corners of our planet. The story begins in the 1870s with the HMS Challenger expedition, one of the first scientific voyages dedicated specifically to exploring the deep ocean. Picture the crew of this converted British naval vessel as they crisscross the Pacific, their ship looking remarkably similar to other vessels of the era, but carrying scientific equipment that was revolutionary for its time. The expedition lasted nearly 4 years and covered almost 70,000 nautical miles, but it was their work in the Western Pacific that would make history. Imagine the scene on deck as the crew prepares for a deep-sea sounding near the island of Guam. There are no sophisticated winches or electronic instruments, just a simple system of weighted ropes and human muscle power. The crew drops a hemp rope over the side with a lead weight attached, and then they wait, sometimes for hours, as the line plays out into the darkness below. The process requires extraordinary patience and skill, as the crew must feel through the rope for the telltale slack that indicates the weight has finally touched bottom. When they finally felt the weight touch bottom, after feeding out over 26,000 feet of line, they had discovered the deepest place on Earth, known at that time, though they had no way of knowing just how much deeper it would prove to be. The achievement was remarkable not just for its scientific significance, but for the human determination it represented. The willingness to spend years at sea, enduring storms, equipment failures, and the endless tedium of deep-sea work, all in pursuit of knowledge about the hidden structure of our planet. The deepest part of the trench was named Challenger Deep in honor of this pioneering expedition, but it would be nearly another century before humans would develop the technology to actually visit this remote place. The challenge wasn't simply one of depth. Submarines had been diving for decades, and by the early 20th century, submersibles could reach depths of several hundred feet. The problem was the extraordinary combination of depth, pressure, and isolation that made the deep trench one of the most technically challenging destinations in the solar system. The first serious attempt to reach the deepest parts of the ocean came in the 1930s with the bathysphere experiments of William Beebe and Otis Barton. Their steel sphere, suspended from a surface ship by a cable, represented a revolutionary approach to deep-sea exploration. Picture these early ocean pioneers, cramped inside their tiny metal ball, barely 6 feet in diameter, with walls over an inch thick to withstand the crushing pressure of the deep. The interior of the bathysphere was Spartanly equipped, with just 2 small quartz windows to peer out at the underwater world, a telephone connection to the surface ship, and basic life support systems that had to function flawlessly for hours at a time. Beebe and Barton could only reach depths of about 3,000 feet, but their achievement proved that humans could survive in the deep ocean if properly protected, and their vivid descriptions of deep-sea life captured the public imagination and inspired a new generation of ocean explorers. The real breakthrough came in the 1950s with the development of the bathyscaphe by Auguste Piccard, a Swiss physicist and inventor who had previously set records for high-altitude balloon flights. The bathyscaphe represented a completely different approach to deep-sea exploration. Instead of being lowered on a cable like the bathysphere, it was a free-diving vehicle that could descend and ascend under its own power. Piccard's design was elegantly simple, yet incredibly sophisticated. The vessel consisted of a large float filled with gasoline, which, unlike air, doesn't compress significantly under pressure, and a small, incredibly strong passenger sphere hanging beneath it. The gasoline provided buoyancy while the sphere protected the human occupants from the crushing pressure of the deep. To dive, the crew would release ballast weights. To ascend, they would drop more weights or release some of the gasoline. The passenger sphere represented the ultimate in precision engineering. Made of forged steel and machined to incredible tolerances, it had to be perfectly spherical to distribute the pressure evenly. Any imperfection, no matter how small, could create a weak point that would fail catastrophically under the enormous pressure of the deep ocean. The sphere's walls were several inches thick, and it was equipped with tiny windows made of specially designed blocks of transparent material that could withstand pressures that would shatter ordinary glass. The culmination of this technological evolution came on January 23, 1960, when Jacques Piccard, Auguste's son, and U.S. Navy Lieutenant Don Walsh climbed into a bathyscaphe called Trieste and began their historic descent toward Challenger Deep. Let's imagine ourselves with them on that historic morning, feeling the mixture of excitement and apprehension that must have filled their small capsule as they sealed the hatch and began sinking into the unknown. The descent was a journey through an alien world that revealed itself in layers. For the first few hundred feet, they could still see the familiar blue of surface waters filtering through their tiny porthole. Marine life was abundant here, schools of fish, jellyfish pulsing through the water, and the occasional larger predator cruising through their field of view. The water was clear and warm, and if not for the steady increase in pressure shown on their instruments, they might have been diving in any tropical reef. As they continued deeper, the water around them gradually changed color, shifting from bright blue to deep indigo and finally to the purple-black of the deep twilight zone. The marine life became stranger and more sparse. Bizarre deep-sea fish with enormous eyes and bioluminescent lures, jellyfish species unlike anything found near the surface, and occasional glimpses of creatures so unusual that they struggled to describe them to the surface team through their voice communication system. The descent took nearly 5 hours, during which Piccard and Walsh watched through their small porthole as the ocean transformed around them into something increasingly alien. The familiar gave way to the extraordinary as they descended through the ocean's layers, each zone revealing its own unique community of specially adapted organisms. They watched their pressure gauges climb steadily, marking their progress toward pressures that had never before been experienced by human beings. The psychological pressure was almost as significant as the physical pressure. They were descending into a realm where no human had ever been, where rescue would be impossible if something went wrong, and where the slightest equipment failure could be fatal. Yet their detailed logs from the dive reveal not panic or fear, but scientific excitement and wonder at the extraordinary world unfolding around them. At 35,113 feet below the surface, nearly 7 miles down, Trieste touched the bottom of Challenger Deep. Pickard and Walsh had become the first human beings to reach the deepest point on Earth's surface, achieving what many had thought impossible. They had traveled farther from the surface of the Earth than commercial airliners fly above it, reaching a place more remote and inaccessible than the surface of the Moon would prove to be just 9 years later. They spent just 20 minutes on the bottom, but in that brief time, they made an extraordinary discovery that challenged the prevailing scientific wisdom of the era. Through their porthole, they observed what appeared to be a flat fish lying on the sediment of the deep sea floor, proving that complex vertebrate life could survive even in Earth's most extreme environment. This single observation revolutionized our understanding of the limits of life on Earth and suggested that even the most extreme environments on our planet might harbor living organisms. The Trieste dive also provided crucial data about the deep ocean environment. The crew recorded temperatures, took water samples, and made observations about the seafloor that would inform deep-sea research for decades to come. They confirmed that the deepest parts of the ocean were not the sterile, lifeless voids that many scientists had predicted, but rather active environments where geological and biological processes continued to operate under conditions unlike anywhere else on Earth. For nearly half a century after the Trieste dive, Challenger Deep remained unvisited by humans. The technical challenges and enormous costs of deep-sea exploration, combined with the shift in scientific priorities toward space exploration during the 1960s and 1970s, meant that robotic vehicles became the primary tools for studying the deep ocean. These unmanned submarines, or remotely operated vehicles, could spend hours or even days in the deep, conducting detailed surveys and collecting samples without risking human lives. However, the dream of returning humans to the deepest places on Earth never completely faded. The next chapter in human exploration of the trench began in the early 2000s with filmmaker and explorer James Cameron, whose passion for both ocean exploration and storytelling drove him to spend years developing a revolutionary new submersible specifically designed to return to Challenger Deep. Cameron's submersible, called Deep Sea Challenger, represented a completely new approach to deep-sea exploration. Picture this remarkable vehicle, a lime-green vertical submarine designed like a torpedo, with Cameron's pilot sphere at the bottom and a tower of scientific equipment and cameras rising above. The design was unlike any previous deep-sea vehicle, optimized for scientific observation and high-definition filming in the deep ocean. The pilot sphere was even smaller than that of Trieste, barely large enough for one person in a cramped fetal position. This compact design was necessary to minimize weight while maximizing strength, but it also meant that Cameron would spend his entire dive in conditions that would challenge even the most experienced claustrophobia sufferers. The sphere was surrounded by cameras, lights, and scientific instruments, all designed to function flawlessly under the enormous pressure of the deep ocean. On March 26, 2012, Cameron made his historic solo dive to Challenger Deep, becoming the third person and first solo explorer to reach the deepest point on Earth. Unlike the brief visit of Trieste, Cameron spent several hours on the bottom, collecting samples, filming the deep environment in high definition, and conducting scientific experiments that had been impossible during earlier visits. Cameron's journey was broadcast live to millions of people around the world, bringing the deep ocean into people's homes for the first time and inspiring a new generation of ocean explorers. His high-definition cameras revealed the deep sea floor in unprecedented detail, showing a landscape that was both alien and beautiful, covered in fine sediment and dotted with the tracks of deep-sea creatures that had passed through the camera's field of view. The samples collected during Cameron's dive revealed new insights into deep-sea biology and geology. Water samples showed unique chemical signatures that provided clues about deep ocean circulation, while sediment samples contained microorganisms that challenged our understanding of the limits of life on Earth. The dive also provided detailed bathymetric data that improved our maps of the deepest places on our planet. But Cameron's dive was just the beginning of a new era of deep-sea exploration. In 2019, explorer Victor Vescovo began a series of dives in his submersible limiting factor, not only reaching Challenger Deep multiple times, but also discovering that it was even deeper than previously measured, nearly 36,200 feet below sea level. Vescovo's repeated visits allowed for extensive scientific sampling and the discovery of new species living in Earth's deepest places. Vescovo's submersible represented another leap forward in deep-sea technology. The limiting factor was designed to be reusable, capable of making repeated dives to full ocean depth with quick turnaround times between missions. This meant that scientists could conduct comprehensive surveys of deep-sea environments, returning to specific locations to monitor changes over time and collect the large sample sets needed for detailed biological and geological analysis. Each of these human journeys to the bottom required extraordinary engineering achievements that pushed the boundaries of materials science, precision manufacturing, and life support systems. The passenger spheres had to be machined to incredible precision from specially selected titanium alloys, with tolerances measured in thousandths of an inch. Any imperfection could create a stress concentration that would lead to catastrophic failure under the enormous pressure of the deep ocean. The life support systems for these deep-sea vehicles represent marvels of engineering miniaturization and reliability. Carbon dioxide scrubbers must remove the gas that would otherwise accumulate and become toxic in the sealed environment of the pilot sphere. Oxygen must be supplied at carefully regulated rates, while temperature and humidity control systems maintain comfortable conditions despite the frigid waters outside. All of these systems must function flawlessly for extended periods in an environment where repair or maintenance is impossible. The navigation and communication systems required for deep-sea exploration represent another category of technological marvel. GPS signals cannot penetrate seawater, so deep-sea vehicles must rely on acoustic navigation systems that use sound waves to determine position relative to surface ships or seafloor transponders. Communication with the surface is maintained through acoustic modems that can transmit voice, data, and even compressed images through miles of water. Perhaps most remarkably, these human expeditions to the deep have revealed that the bottom of the Mariana Trench is not the sterile, unchanging place many had imagined. Instead, it's a dynamic environment where geological processes continue to shape the seafloor, where unique ecosystems thrive in conditions that challenge our understanding of life's limits, and where new discoveries await each visitor who makes the journey to Earth's most remote frontier. The human quest to reach the bottom of the Mariana Trench represents more than just technological achievement. It embodies our species' irrepressible curiosity about our planet and our drive to explore the unknown. Each descent into the abyss has expanded our understanding not only of the deep ocean, but of life's possibilities, Earth's geological processes, and our own capabilities as explorers and scientists. As we continue to develop new technologies for deep-sea exploration, including advanced autonomous vehicles and even more sophisticated manned submersibles, the Mariana Trench remains one of our planet's most active frontiers. Each visit brings new discoveries, new questions, and new appreciation for the extraordinary complexity and beauty of the deepest places on Earth. The trench continues to challenge us, inspire us, and remind us that even on our well-explored planet, there are still frontiers waiting for the next generation of explorers brave enough to venture into the abyss. The exploration of the Mariana Trench has yielded some of the most extraordinary and paradigm-shifting scientific discoveries of the past century, each revelation fundamentally reshaping our understanding of life, geology, chemistry, and the very nature of our planet. As we settle into our comfortable imaginary research station floating above the trench, surrounded by sophisticated monitoring equipment and laboratories filled with samples from the deep, let's explore the remarkable findings that have emerged from this underwater laboratory and consider the profound mysteries that continue to intrigue scientists around the world. One of the most groundbreaking discoveries has been the identification of entirely new forms of life that exist nowhere else on Earth, organisms so unique and specialized that they've forced scientists to completely reconsider what we thought we knew about the limits and possibilities of biology. In 2014, researchers made headlines worldwide when they discovered a new species of snailfish living at depths of over 26,000 feet, deeper than any vertebrate had ever been found before, in a realm where scientists had believed complex multicellular life simply could not exist. These ethereal creatures, with their translucent bodies that seem to glow in the submersible's lights, and their oversized heads that house brains adapted to process information in an eternally dark world, have evolved unique adaptations that challenge our basic understanding of vertebrate physiology. Their discovery forced scientists to completely reconsider the depth limits for vertebrate life and opened up new questions about how complex organisms can adapt to such extreme conditions. The snailfish found in Challenger Deep possess cellular adaptations that border on the miraculous. Their proteins are folded in unique, three-dimensional configurations that remain stable under crushing pressures that would denature most biological molecules. Their cell membranes are composed of specialized lipids that maintain their integrity and flexibility under conditions that would turn normal cellular structures into rigid, non-functional masses. Most remarkably, their bones have evolved to be flexible rather than rigid, allowing them to withstand the enormous pressure while still providing structural support for their bodies. Even more remarkable has been the discovery of microbial life forms that challenge our basic understanding of biology and the conditions necessary for life to exist. Deep in the sediments of Challenger Deep, scientists have found bacteria and archaea that derive energy from chemical processes, involving sulfur, methane, and other compounds in ways that were unknown to science just a few decades ago. These organisms represent some of the oldest forms of life on Earth, evolutionary descendants of the first living things that arose in our planet's ancient oceans when the atmosphere contained no oxygen and life had to find alternative ways to generate energy. Some of these microorganisms have been found living within the rocks and sediments of the trench floor, in spaces so small and under pressures so extreme that their very existence challenges our understanding of what constitutes a livable environment. They've evolved metabolic pathways that allow them to extract energy from chemical compounds that would be toxic to most life forms, creating complex ecosystems based entirely on chemical energy rather than sunlight. The geological discoveries emerging from the Mariana Trench have been equally stunning, revealing that this deepest place on Earth is far from the static, unchanging environment that scientists once assumed it to be. Advanced sonar mapping and direct observation have shown that the deepest parts of the trench are geologically active, with ongoing processes that continue to reshape the seafloor in real time. Scientists have documented underwater earthquakes that, while unfelt at the surface, regularly occur within the trench system. These seismic events, some measuring significant magnitudes on the Richter scale, indicate that the tectonic forces that created the trench continue to operate today. Researchers have also documented massive underwater landslides that can move millions of tons of sediment in a matter of hours, completely reshaping large areas of the seafloor and burying existing ecosystems under layers of displaced material. One of the most significant geological discoveries has been the identification of active serpentinization processes occurring within the trench. This fascinating chemical process occurs when seawater comes into contact with certain minerals in the oceanic crust, particularly olivine and pyroxene, under the extreme pressure and temperature conditions found in the deep trench. The reaction produces hydrogen gas, methane, and other compounds that can serve as energy sources for chemosynthetic organisms, creating biological oases in the deep ocean. The serpentinization process has profound implications for our understanding of both geology and biology. It creates chemical conditions that can support unique forms of life in the absence of any connection to surface photosynthesis, and it may represent one of the ways that life first evolved on Earth billions of years ago. This process essentially turns rock and water into the basic chemical building blocks needed for life, suggesting that similar processes might support life in the subsurface oceans of icy moons like Europa and Enceladus. Scientists have also made surprising and important discoveries about water circulation in the deepest parts of the ocean, revealing connections between the Mariana Trench and global ocean systems that were previously unknown. Rather than being a stagnant pool of water sitting motionless at the bottom of the sea, the deepest waters of the trench are part of a vast, complex circulation system that connects the deepest places on Earth with surface waters in polar regions thousands of miles away. This deep water circulation, driven by differences in temperature and density, means that water that sinks in the Arctic or Antarctic oceans eventually makes its way to the deep trenches, carrying dissolved nutrients, oxygen, and even pollutants on journeys that can take decades or centuries to complete. This discovery has revealed that the deepest parts of the ocean are intimately connected to global climate patterns, ocean health, and atmospheric conditions, making the deep trenches crucial components of Earth's overall environmental system. The study of sediments in the Mariana Trench has opened remarkable windows into Earth's ancient past, revealing details about our planet's history that are preserved nowhere else. The layers of sediment on the trench floor contain microscopic fossils, volcanic ash from ancient eruptions, and chemical signatures that tell stories of past climate changes, ocean chemistry fluctuations, and even asteroid impacts that occurred millions of years ago. These deep-sea sediments are like pages in an enormous book of Earth's history, with each layer representing a different chapter in our planet's story. The oldest sediments, buried deep beneath hundreds of feet of more recent deposits, contain evidence of ocean conditions that existed when dinosaurs roamed the Earth. The youngest sediments, still accumulating on the seafloor today, preserve records of recent climate changes and human impacts on the global environment. Scientists have discovered that the rate of sedimentation in different parts of the trench varies dramatically, creating a complex temporal and spatial record of environmental changes. Some areas accumulate sediment rapidly, preserving high-resolution records of short-term environmental fluctuations. Other areas accumulate sediment very slowly, creating compressed records that span millions of years, but with less temporal detail. One of the most concerning and unexpected recent discoveries has been the presence of human pollution even in the deepest, most remote parts of the ocean. Plastic debris, chemical pollutants, and even radioactive materials have been found in the deepest trenches, revealing that human impact on the environment extends even to the most inaccessible corners of our planet. This finding has profound implications for our understanding of how pollutants move through ocean systems and accumulate in unexpected places. The discovery of microplastics in Challenger Deep was particularly shocking to researchers. These tiny fragments of plastic, many smaller than a grain of rice, have somehow made their way from the surface world to the deepest places on Earth, where they're being ingested by deep-sea organisms and incorporated into the deep-sea food web. The implications of this contamination are still being studied, but it's clear that even the most remote environments on our planet are not isolated from human activities. Chemical pollutants, including persistent organic compounds and heavy metals, have also been detected in deep trench sediments and in the tissues of deep-sea organisms. Some of these pollutants may have reached the deep ocean through atmospheric transport, carried by winds across vast distances before settling into the ocean and eventually sinking to the deepest places. Others may have been transported by deep ocean currents or through the food web as contaminated organic matter sank from surface waters. Researchers have also discovered that the Mariana Trench plays a crucial and previously unrecognized role in the global carbon cycle. The trench acts as a significant carbon sink, trapping organic matter and carbon dioxide in its deepest sediments, where it can remain locked away from the atmosphere for millions of years. Understanding these deep-sea carbon storage processes is essential for predicting how ocean systems will respond to increasing atmospheric carbon dioxide levels and climate change. The deep trench stores carbon through several mechanisms. Organic matter that sinks from the productive surface waters above becomes buried in the deep sediments, where the cold temperatures and low oxygen conditions slow decomposition and allow carbon to accumulate over long periods. The extreme pressure at depth also affects how carbon dioxide behaves in seawater, potentially allowing more CO2 to be stored in the deep ocean than previously calculated. The discovery of unique mineral formations in the trench has revealed new insights into the chemistry of extreme environments and the geological processes that operate under conditions unlike anywhere else on Earth. Scientists have found mineral deposits that form only under the specific combination of extreme pressure, low temperature, and unique chemical conditions found in the deepest trenches. These minerals, many of which are unknown from terrestrial environments, may hold clues to understanding similar processes on other planets and moons in our solar system. The conditions in the deep ocean trenches may be analogous to those found in the subsurface oceans of Europa, Enceladus, and other icy bodies, making the study of deep trench mineralogy relevant to astrobiology and planetary science. Some of the most exciting mineral discoveries have been associated with hydrothermal vents in the trench system, where hot water interacting with cold seawater creates unique chemical conditions that promote the formation of exotic mineral assemblages. These include sulfide minerals that form towering chimney structures, carbonate deposits that precipitate from the unique water chemistry, and even native metals that form under the reducing conditions of the deep sea floor. Biologists studying the trench have made remarkable discoveries about the absolute limits of life on Earth, finding organisms thriving in conditions that push the boundaries of what science previously thought was possible for living systems. The organisms living in the deepest parts of the ocean have evolved proteins and cellular structures that maintain their function under pressure levels that would destroy most biological molecules. Understanding how these proteins work has implications far beyond marine biology, offering insights into protein folding, enzyme function, and the fundamental biochemistry of life that could revolutionize biotechnology and medicine. Some deep-sea proteins remain stable and functional under conditions that would cause surface proteins to unfold and become useless, suggesting new approaches to developing industrial enzymes and pharmaceutical compounds that must function under harsh conditions. The reproductive strategies of deep-sea organisms have also revealed fascinating adaptations to life in extreme isolation. Many deep trench species have evolved the ability to reproduce asexually when mates are unavailable, while others have developed extraordinary sensory systems that allow them to detect potential partners across vast distances in the darkness of the abyss. Yet for all these remarkable discoveries, the Mariana Trench continues to hold many secrets that challenge our understanding and fuel ongoing research. Scientists estimate that we've explored less than 5% of the deep ocean, and new species are discovered with nearly every expedition to the trench. The true extent of biodiversity in these deep environments remains unknown, and researchers suspect that many more unique ecosystems and evolutionary experiments await discovery in the deepest places on Earth. One of the most intriguing ongoing mysteries involves the detection of mysterious acoustic signals in the deep ocean that have never been fully explained. Hydrophones lowered into the trench have detected strange sounds, some low-frequency rumbles, others resembling metallic noises or organic calls, that suggest the deep ocean is far more acoustically active than previously imagined. Some of these sounds may be geological in origin, created by the movement of sediments or the settling of underwater landslides. Others may be biological, representing the communication calls of deep-sea organisms that remain undiscovered. The geological processes occurring at the deepest levels of the trench continue to puzzle scientists. While we understand the basic mechanics of subduction that created the trench, the detailed processes occurring at the deepest levels, where oceanic crust is being recycled back into the Earth's mantle, remain mysterious. How does the oceanic crust behave under such extreme conditions? What happens to water and organic matter as they're carried deep into the Earth's interior? These questions have profound implications for understanding how our planet recycles its surface materials and maintains its long-term geological stability. Perhaps most intriguingly, the study of extremophile organisms in the Mariana Trench has implications that extend far beyond our understanding of life on Earth. If life can thrive in the crushing depths of Earth's deepest trenches, under conditions of extreme pressure, perpetual darkness, and unique chemistry, it dramatically expands the range of environments where we might expect to find life elsewhere in the universe. The icy moons of Jupiter and Saturn, Europa, Enceladus, and others, with their deep subsurface oceans hidden beneath frozen surfaces, suddenly seem much more promising as potential habitats for life. The conditions in these alien oceans may be similar in many ways to those found in Earth's deepest trenches: high pressure, darkness, and chemical energy sources that could support chemosynthetic life forms. The trench also holds mysteries related to earthquake activity and tsunami generation that have important implications for understanding seismic hazards throughout the Pacific region. Scientists are working to understand how the ongoing subduction process in the Mariana region affects seismic activity thousands of miles away, and whether the deep geological processes occurring in the trench can influence earthquake patterns across vast distances. The relationship between deep trench processes and surface phenomena remains poorly understood. Do changes in subduction rates affect volcanic activity in the Mariana Islands? Can deep-sea earthquakes trigger surface seismic events? These questions are crucial for understanding the interconnected nature of geological processes and for assessing seismic hazards in the Pacific region. Another fascinating area of ongoing research involves the unique chemistry of deep trench waters and sediments. Scientists have discovered that the extreme conditions in the deepest parts of the ocean create chemical environments that exist nowhere else on Earth, with unique combinations of pressure, temperature, and dissolved substances that may preserve records of ancient ocean conditions and provide insights into how Earth's oceans have evolved over billions of years. The deep trench environment may also serve as a natural laboratory for understanding chemical processes that occur in other extreme environments, both on Earth and elsewhere in the solar system. The high-pressure, low-temperature chemistry of the deep ocean may be similar to conditions found in the interiors of large icy moons, making the study of deep trench chemistry relevant to astrobiology and planetary science. The Mariana Trench continues to serve as a natural laboratory for understanding extreme environments, offering insights that extend far beyond oceanography into fields ranging from astrobiology to materials science, from climate science to evolutionary biology. Each new expedition brings fresh discoveries that challenge our assumptions and deepen our understanding of how complex systems operate under extreme conditions. The ongoing study of this deepest place on Earth also raises profound questions about the interconnectedness of our planet's systems and the extent of human impact on even the most remote environments. As we continue to discover the ways that surface processes affect deep ocean environments and vice versa, we're gaining a better appreciation for the complex web of connections that link every part of our planet's system. Perhaps most importantly, the scientific exploration of the Mariana Trench continues to reveal that our planet still holds countless secrets, even in an age when satellite imagery can map every square meter of Earth's surface. The deep ocean remains one of our planet's last great frontiers, promising discoveries that will challenge and inspire scientists for generations to come, reminding us that the spirit of exploration and discovery that drives human knowledge remains as relevant today as it was when the first explorers set out to map the unknown corners of our world. The quest to explore and understand the Mariana Trench has driven some of the most remarkable technological innovations in human history, pushing the boundaries of engineering, materials science, and human ingenuity in ways that rival the challenges of space exploration. As we imagine ourselves in a cutting-edge research facility overlooking the Pacific, surrounded by the sophisticated equipment that makes deep-sea exploration possible, let's discover how human creativity and determination have created the tools needed to survive and work in one of the most challenging environments in our solar system. The story of deep-sea technology begins with a fundamental challenge that has driven innovation for over a century, creating vessels that can protect human life under pressures that would instantly crush any ordinary structure. The passenger spheres used in deep-sea submersibles represent marvels of precision engineering that push materials and manufacturing techniques to their absolute limits. These perfect spheres, typically made from titanium alloys or specially forged steel, must be machined to tolerances measured in thousandths of an inch, precision that rivals the most sophisticated aerospace applications. Picture the construction of a modern, deep-sea submersible sphere. Massive blocks of specially selected titanium, chosen for their unique combination of strength, lightness, and resistance to corrosion, are slowly carved away by computer-controlled machines working with diamond-tipped tools. The process can take weeks or even months, with the sphere being repeatedly measured and tested at each stage to ensure perfect roundness and uniform wall thickness. The sphere's diameter can vary by no more than the thickness of a human hair. Any deviation from perfect spherical geometry would create stress concentrations that could lead to catastrophic failure under the enormous pressure of the deep ocean. The interior surface must be mirror smooth, without any scratches, tool marks, or imperfections that could serve as starting points for cracks under stress. Even the viewports, thick windows of synthetic sapphire or specialized glass that allow occupants to observe the underwater world, must be perfectly fitted and sealed. These transparent barriers, often several inches thick and costing tens of thousands of dollars each, are strong enough to hold back the crushing pressure of the abyss, while remaining optically clear enough to provide crisp, undistorted views of the deep-sea environment. The manufacturing process for these viewports represents its own technological marvel. The sapphire or specialized glass must be grown or formed under carefully controlled conditions, then ground and polished to optical perfection. The sealing systems that hold them in place must be absolutely reliable, using advanced materials and engineering techniques developed specifically for deep-sea applications. The life support systems for these deep-sea vehicles represent another triumph of engineering miniaturization and reliability. In the cramped confines of a submersible sphere, where space is measured in cubic feet rather than cubic meters, every system must be redundant, reliable, and incredibly efficient. Carbon dioxide scrubbers use specialized chemical filters, often based on lithium hydroxide or other advanced compounds, to remove the gas that would otherwise accumulate and become toxic to the occupants. These scrubbing systems must function flawlessly for hours or even days, continuously processing the air inside the sphere and removing not just carbon dioxide, but also excess moisture and other contaminants that could affect the health and performance of the crew. The systems are designed with multiple backups and fail-safes, ensuring that even if one component fails, the crew will have adequate life support to complete their mission and return safely to the surface. Oxygen is supplied through carefully regulated systems that must maintain proper atmospheric composition under changing pressure conditions. As the submersible descends and the external pressure increases, the life support systems must adjust to maintain breathable air inside the sphere without allowing dangerous pressure differentials to develop. These systems often use a combination of stored oxygen and chemical oxygen generators that can produce fresh oxygen as needed during extended missions. Temperature control systems face the unique challenge of maintaining comfortable conditions inside the sphere despite the frigid waters outside and the heat generated by electronic equipment and human occupants. Advanced insulation materials and carefully designed heating and cooling systems ensure that the crew can work effectively even during missions lasting many hours in near-freezing deep water. Modern deep-sea submersibles are equipped with remarkable propulsion systems that allow precise maneuvering in the three-dimensional environment of the deep ocean. Multiple thrusters, powered by high-capacity battery systems, can push the vehicle in any direction with the precision of a spacecraft docking with a space station. The thruster systems are designed to operate under extreme pressure, while providing enough power to overcome ocean currents and maintain position above interesting seafloor features. These propulsion systems represent significant engineering challenges in their own right. The thrusters must be completely sealed against the intrusion of seawater while operating under crushing pressure. The electrical systems that power them must be insulated and protected against the corrosive effects of seawater and the extreme pressure of the deep ocean. Advanced battery technologies, often based on lithium-ion or other high-energy density chemistries, provide the power needed for extended operations while fitting within the strict weight and space limitations of the submersible. The lighting systems used in deep-sea exploration have evolved from simple incandescent spotlights to sophisticated arrays of LED lights that can illuminate the seafloor with the brightness of daylight. These lights must be designed to withstand crushing pressure while producing the intense illumination needed for photography, filming, and scientific observation in the eternal darkness of the deep. Modern LED lighting systems offer several advantages over earlier technologies. They produce less heat, reducing strain on the submersible's cooling systems, consume less power, extending mission duration, and provide better color rendition, important for scientific photography and specimen identification. The lights are often arranged in carefully designed patterns to minimize shadows and provide even illumination across the submersible's field of view. Perhaps most remarkably, modern deep-sea vehicles carry extensive arrays of scientific equipment packed into spaces no larger than a small closet. High-definition cameras capable of recording in 4K or even 8K resolution capture images and video with clarity that reveals details invisible to earlier generations of underwater explorers. These camera systems must be specially designed to function under extreme pressure while maintaining optical quality and mechanical reliability. Specialized sensors measure temperature, pressure, chemical composition, pH levels, dissolved oxygen content, and dozens of other environmental parameters with precision that rivals the best laboratory instruments. These sensors must be calibrated to function accurately under the extreme conditions of the deep ocean, where pressure can affect the behavior of electronic components and chemical sensors in unexpected ways. Water sampling systems allow scientists to collect pristine samples from specific depths and locations, often preserving them under pressure to maintain the integrity of deep-sea organisms and chemical compounds that would be altered by decompression. These systems use sophisticated valves and containers designed to capture and seal water samples without contamination from shallower depths or the submersible's own systems. Sediment sampling equipment, including corers and grab samplers, allows scientists to collect samples of the seafloor and the organisms that live within it. These tools must be operated remotely through manipulator arms while maintaining precise control and avoiding contamination of the samples. Robotic arms, controlled by the pilot through joysticks and computer interfaces, can collect samples with surgical precision, manipulating objects on the seafloor with the dexterity of a human hand. These manipulator systems represent extraordinary achievements in robotics and control systems, allowing operators to perform delicate tasks while separated from their work by miles of water and layers of technological complexity. The arms themselves must be built to withstand extreme pressure while maintaining the flexibility and precision needed for scientific work. The control systems must provide enough feedback and responsiveness to allow operators to perform tasks as delicate as picking up individual specimens or as demanding as drilling core samples from hard rock surfaces. The communication systems that connect deep-sea vehicles to the surface represent another technological marvel that enables real-time coordination between submersible crews and surface support teams. Acoustic modems use sound waves to transmit data through miles of water, allowing real-time communication between the submersible and support ships on the surface. These acoustic communication systems can transmit not only voice communications, but also telemetry data, navigation information, and even compressed images and video. The systems must account for the unique acoustic properties of the deep ocean, where sound travels at different speeds depending on water temperature, pressure, and salinity, and where acoustic signals can be distorted by seafloor topography and water column structures. More advanced communication systems use fiber optic cables to provide high-bandwidth connections between tethered vehicles and surface support ships. These systems can transmit real-time high-definition video, detailed sensor data, and control signals with minimal delay, allowing surface-based scientists to participate directly in deep-sea exploration and research. Navigation in the featureless environment of the deep ocean requires sophisticated systems that work without GPS or visual landmarks. Modern submersibles use arrays of acoustic beacons placed on the seafloor to create underwater navigation networks, similar to jeeps but using sound instead of radio waves. These acoustic positioning systems can determine the submersible's location with accuracy measured in meters, allowing precise navigation and the ability to return to specific locations of scientific interest. Inertial guidance systems, similar to those used in spacecraft and aircraft, track the vehicle's position and movement with remarkable precision using accelerometers and gyroscopes that can detect the smallest changes in motion. These systems allow pilots to navigate complex underwater terrain and maintain position even when acoustic navigation signals are blocked by seafloor topography. The development of remotely operated vehicles, ROVs, has revolutionized deep-sea research by allowing scientists to explore dangerous environments without risking human lives. These unmanned submarines, connected to surface ships by fiber optic cables, can spend days or weeks in the deep ocean, conducting detailed surveys and collecting samples under direct control from surface-based pilots and scientists. The most advanced carry the same sophisticated scientific equipment as manned submersibles, but with the added advantage of being able to work continuously without the constraints of human life support. They can be deployed in conditions that would be too dangerous for manned vehicles, such as active volcanic areas or regions with strong currents, and they can remain on station for extended periods to monitor long-term changes in deep-sea environments. Recent innovations have produced autonomous underwater vehicles, AUVs, that can operate independently for months at a time, following pre-programmed routes through the deep ocean while collecting data and samples. These robotic explorers use advanced artificial intelligence systems to navigate complex underwater terrain, avoid obstacles, and make decisions about where to collect samples and data. Some AUs are designed to hibernate on the seafloor between missions, conserving power while monitoring long-term changes in the deep-sea environment. These vehicles can be programmed to wake up periodically to take measurements, communicate with surface stations, or respond to changes in environmental conditions. The sample collection and preservation systems used in deep-sea research represent elegant solutions to complex challenges that have no parallel in terrestrial science. Special pressurized containers maintain samples at deep-sea pressure during their journey to the surface, preventing deep-sea organisms from being damaged by decompression and preserving the chemical integrity of water and sediment samples. Temperature-controlled storage systems keep biological samples viable for laboratory analysis, often using advanced refrigeration systems that can maintain precise temperatures even under the challenging conditions of a research vessel at sea. Automated preservation systems can fix samples in chemical preservatives immediately after collection, ensuring that delicate biological structures are preserved before they can begin to deteriorate. Advanced imaging technologies have transformed our ability to document and study the deep ocean in ways that would have seemed magical to earlier generations of ocean explorers. High-resolution cameras can capture images with such clarity that scientists can identify individual bacteria on the seafloor, while specialized lighting systems reveal the true colors of deep-sea life that have never been illuminated by natural sunlight. Laser measurement systems create precise, three-dimensional maps of underwater terrain, allowing researchers to track changes in seafloor topography over time and to measure the size and shape of deep-sea organisms and geological features with millimeter precision. These systems can create detailed digital models of deep-sea environments that allow scientists to study underwater landscapes with the same precision they might use to study terrestrial features. Multi-beam sonar systems can map vast areas of the seafloor in extraordinary detail, revealing underwater mountains, valleys, and geological features that were completely unknown just decades ago. These systems can penetrate seafloor sediments to reveal buried structures and geological layers that provide insights into the deep ocean's history and evolution. The data processing and analysis systems that support deep-sea research represent some of the most sophisticated computer technologies available. Artificial intelligence algorithms help identify new species in thousands of hours of video footage, comparing morphological features and behaviors to vast databases of known organisms and flagging potential new discoveries for further study. Advanced modeling software allows scientists to simulate deep-sea processes and predict how they might change over time in response to climate change, pollution, or other environmental factors. These models integrate data from multiple sources: temperature and pressure sensors, chemical analyzers, biological surveys, and geological observations to create comprehensive pictures of deep-sea ecosystem function and health. Perhaps most impressively, The integration of all these technologies into working deep-sea exploration systems requires extraordinary coordination and reliability that has no parallel in most other fields of science and engineering. Every component must function perfectly in an environment where repair or replacement is impossible, where rescue may be impossible, and where the consequences of failure can be catastrophic. The engineering teams that design and build these systems must anticipate every possible failure mode and design redundant backup systems that can keep explorers safe even when primary systems fail. They must test their designs under conditions that simulate the extreme environment of the deep ocean, using pressure chambers, thermal cycling systems, and corrosion testing that pushes materials and components to their limits. The costs and complexity of deep-sea exploration technology mean that international cooperation has become essential for advancing our understanding of the deep ocean. Research institutions around the world share vessels, equipment, and expertise, creating global networks of deep-sea exploration capability that pool resources and knowledge to tackle challenges that no single institution could address alone. This collaboration has accelerated the pace of discovery and ensured that the technological marvels developed for deep-sea research benefit scientists and explorers everywhere. Innovations developed for deep-sea exploration often find applications in other fields, from aerospace engineering to medical devices, demonstrating the broader value of pushing technological boundaries in pursuit of scientific knowledge. As we continue to push the boundaries of deep-sea exploration, new technologies are constantly being developed that promise to revolutionize our ability to study and understand the deep ocean. Advanced materials, including carbon nanotubes and graphene-based composites, promise to create stronger, lighter submersibles that can dive deeper and carry more scientific equipment. Improvements in battery technology, driven partly by developments in electric vehicles and renewable energy storage, will extend the range and duration of deep-sea missions. New energy storage systems based on fuel cells, advanced lithium batteries, or even nuclear power sources could enable autonomous vehicles to operate for months or years without returning to the surface. Artificial intelligence and machine learning technologies are beginning to enable autonomous systems that can make complex decisions about scientific sampling and exploration without human guidance. These systems could identify interesting specimens or geological features automatically, collect appropriate samples, and even conduct preliminary analysis of their findings before returning to the surface. The technological marvels that make deep-sea exploration possible represent humanity at its most ingenious and persistent, embodying our species' determination to understand our world despite the most challenging obstacles. Each system, from the smallest pressure sensor to the most sophisticated submersible, embodies years of research, development, and testing by teams of engineers and scientists working at the very limits of what technology can achieve. Together, these technologies form the foundation that allows us to explore and understand one of the most challenging and fascinating environments in our solar system. They represent not just solutions to engineering problems, but expressions of human curiosity and determination that enable us to venture into realms that would otherwise remain forever beyond our reach, bringing back knowledge and understanding that enriches our appreciation of the remarkable world we inhabit. As our gentle journey through the Mariana Trench comes to a close, we find ourselves floating peacefully in our imagination, suspended between the familiar world of the surface and the extraordinary realm of the deep that we've explored together tonight. Like ancient mariners returning from distant shores with tales of wonder and discovery, we carry with us not just knowledge, but a profound sense of awe about the hidden complexities and unexpected beauty that exist in the deepest corners of our own planet. The story of the Mariana Trench reminds us that Earth still holds mysteries in its deepest places, that beneath the waves lies a world as alien and fascinating as anything we might find on distant planets or in the far reaches of space. In those crushing depths where no sunlight has ever penetrated, where pressure would instantly compress our familiar world into unrecognizable forms, we've discovered that life finds not just a way to survive, but ways to flourish in forms so extraordinary they expand our very definition of what life can be. We've journeyed through geological time to witness the slow, patient forces that carved this deepest canyon from the ocean floor, coming to understand that the solid ground beneath our feet and the seemingly permanent features of our world are part of a dynamic, ever-changing system that operates on time scales that humble human comprehension. The Mariana Trench stands as a testament to the power of time and pressure working together over millions of years, showing us how forces that seem imperceptible on human timescales can create some of the most dramatic landscapes on our planet. In the remarkable creatures we've encountered, from the microscopic extremophiles that thrive in conditions that would destroy most life, to the ethereal deep-sea fish that swim in eternal darkness, to the giant tube worms that have partnered with bacteria to create their own food from chemicals, we've seen evolution's endless creativity and adaptability. These organisms haven't just adapted to extreme conditions, they've embraced them, developing biological solutions to challenges that inspire both scientists and engineers working at the cutting edges of technology and medicine. Their very existence suggests that life may be far more resilient, creative, and widespread in the universe than we once believed. If complex organisms can thrive in the crushing depths of Earth's deepest trenches, under conditions of extreme pressure, perpetual darkness, and unique chemistry, it opens our minds to the possibility that life might exist in the subsurface oceans of icy moons, in the deep crustal rocks of other planets, or in environments throughout the cosmos that we're only beginning to imagine. The human quest to reach these depths speaks to something fundamental and inspiring in our nature, our irrepressible curiosity about the unknown and our determination to push beyond the boundaries of what seems possible. Each descent into the abyss, from the pioneering voyage of the Trieste, with its brave crew cramped in their tiny sphere, to the sophisticated explorations of today, with their high-definition cameras and advanced scientific instruments, represents not just technological achievement, but a profound expression of our desire to understand our place in the natural world. These expeditions remind us that exploration and discovery remain as important today as they were when the first humans ventured beyond familiar territories. The deep ocean represents one of the last great frontiers on our own planet, a realm that challenges us technically, scientifically, and philosophically, pushing us to develop new technologies, new ways of thinking about life, and new appreciation for the complexity and interconnectedness of our world. The scientific discoveries emerging from the Mariana Trench continue to reshape our understanding of biology, geology, chemistry, and the interconnected systems that govern our planet. These findings remind us that the deep ocean isn't separate from our everyday world, but intimately connected to it through vast currents that circulate nutrients and heat around the globe, through chemical cycles that affect the atmosphere and climate, and through biological processes that influence the health of ocean ecosystems everywhere. The realization that human pollution has reached even the deepest places on Earth serves as a sobering reminder of our species' impact on the planet and our responsibility as stewards of the global environment. The presence of plastic debris and chemical contaminants in Challenger Deep shows us that no place on Earth is truly isolated from human activities, and that the health of these remote ecosystems is ultimately connected to the choices we make in our daily lives. Perhaps most humbling is the recognition that we've barely begun to explore these depths, that each expedition reveals new species, new geological process, new mysteries that challenge our assumptions about how the world works. The Mariana Trench serves as a reminder that our planet still holds countless secrets, waiting to be discovered by future generations of explorers, scientists, and curious minds willing to push the boundaries of human knowledge and capability. The technological marvels that make deep-sea exploration possible, the precisely engineered submersibles, the sophisticated life support systems, the advanced cameras and scientific instruments, represent human ingenuity and persistence at their finest. These technologies embody our species' remarkable ability to solve complex problems, to work together across disciplines and institutions, and to create tools that extend our senses and capabilities into realms that would otherwise remain forever beyond our reach. As we let these thoughts settle like sediment drifting slowly through the water column, we might reflect on what the existence of such places means for our understanding of Earth and our place within the larger cosmos. The Mariana Trench offers us a different perspective on depth and height, pressure and release, darkness and illumination, reminding us that there are many ways to experience and understand our world beyond our familiar surface existence. In a world where we often focus on reaching higher, moving faster, and shining brighter, there's something profoundly peaceful and grounding about contemplating this deep, slow, patient realm where time moves differently and silence reigns supreme. The deep ocean teaches us about the value of persistence, adaptation, and finding beauty and meaning in the most unlikely places. The trench also reminds us of the importance of maintaining our sense of wonder and curiosity about the natural world. In an age when it sometimes seems that everything has been discovered and mapped, the deep ocean stands as proof that mystery and discovery are still possible, that our world still has the power to surprise and inspire us with its complexity and beauty. Tonight, as you prepare for sleep, you might imagine yourself once more in that comfortable submersible, gently rising from the depths toward the surface, carrying with you the quiet wisdom of the abyss. The crushing pressure gradually eases as you ascend. The eternal darkness slowly gives way to the faint glow of distant surface light, and the extraordinary creatures of the deep fade back into the darkness from which they emerged. But the memory of that deep world remains, a reminder that beneath the surface of the everyday, profound mysteries and extraordinary beauty continue to exist, waiting patiently for those curious and brave enough to seek them out. The Mariana Trench will continue its ancient descent into the Earth's interior, continue to host its remarkable communities of life, continue to hold secrets that will inspire and challenge human understanding for generations to come. In the gentle rhythm of your breathing as you settle into sleep, you might hear an echo of the slow, deep currents that flow through Earth's deepest places, carrying ancient waters on journeys that span decades and continents, connecting the most remote corners of our planet in an endless circulation of life and renewal. In the darkness behind your closed eyes, you might sense something of that profound, peaceful darkness where life has learned to create its own light and meaning, where existence continues in forms so beautiful and alien they seem like gifts from another world. The Mariana Trench stands as a monument to the extraordinary diversity and resilience of our planet, a reminder that even in the most extreme environments, remarkable things are not only possible, but actively happening. As you drift off to sleep, carry with you this sense of wonder about the hidden depths of our world, and perhaps dream of the discoveries yet to be made in the deepest, most mysterious places on Earth. Rest well, fellow explorer, knowing that you've journeyed tonight to one of the most remarkable places in our solar system without leaving the comfort of your imagination. The abyss will be there tomorrow, patient and eternal, continuing its silent work of humbling and inspiring all who dare to contemplate its depths. In the morning, the familiar surface world will welcome you back, but you'll carry with you forever the knowledge that far below, in Earth's deepest places, extraordinary worlds continue to thrive in ways we're only beginning to understand. The deep ocean reminds us that our planet is far more complex, mysterious, and beautiful than we often realize in our daily lives, and that the spirit of exploration and discovery that drives human knowledge remains as vital and rewarding today as it has ever been. In the depths of the Mariana Trench, in the darkness and pressure that seem so hostile to life, we've found not emptiness but abundance, not simplicity but extraordinary complexity, not an ending but a beginning of new understanding about the remarkable world we call home.